Alright, welcome back. This is the circular motion 2 video. This is the second video problem on those slides. I should be able to solve the last two problems with this video. In this question, we have a coefficient of friction between the car and the roadway. It says determine the maximum speed at which the car can maneuver around this radius. So it says beginning with a free body diagram. Well, let's do that then. So here we go. So if we look at this car, this is kind of like a three-dimensional top-down kind of thing. So straight down, as always, we can add gravity acting on the car. And then straight up, pushing from the surface, we can have our normal. Now, in order for this car to even make a curve, there must be something pointing toward the center. That's the definition of circular motion. Force must cause it to go in a circle. And in this case, it's going to be our friction. If you think about it, without friction, if this was just an ice field, you would go straight. If you have the unfortunate experience, you'll notice that when you're driving, especially in icy or snowy weather, that turning becomes difficult. Your car will just keep going straight, and you need the friction to actually make your turns. So the question is find velocity. So automatically, when I think of this, I know the force centripetal can be modeled, or the net force of a circle is mv squared over r, which is where we're going to get our velocity. I'll do this in black ink, like that. But we need a little more information. Or what we can say is that the friction is causing the circle motion, just like that, which is what we're going to say. So remember, force friction is force normal times mu, which is equal to mv squared over r. Now, something that's really nice about this is we're on a level surface, so force normal in this problem does equal to the magnitude of the gravity, and magnitude I mean just the number. In other words, we can set it equal to that. So then we could do this. mg mu equals mv squared over r, like that. And the beauty of doing that is that the mass of the car cancels. So we get gu equals v squared over r. Or, as you can see, rgu, so I moved the r up, and then if we square root it, we can get the velocity. So, with that said, we get the velocity by taking the square root of those three things. So the radius of curvature is 25 meters, pretty big curve. The acceleration due to gravity is, well, 9.81. And then mu we have is 0.85, like that. And here we go. 25 times 9.81 times 0.85, square root of the answer, 14.44 meters per second. And there you have it. The very interesting thing about this is this says basically that in order to go in a circle with this particular velocity, the only things that really matter are the radius of the circle and how much friction or coefficient of friction, not mass. Pretty neat. So this could be a truck, a person, a small child going in a circle. They will all have the same speed. The things that do matter are the radius and the coefficient of friction. Now I didn't mention the force, the gravitational acceleration, because that's the same on the planet. So if we went to a different planet, this would change. But that's it. That's it for that problem. Let's move on. Ooh, this is the banked curves. This is why highways bank their curves, so that you can go faster as you turn. So, a little bit about that. So, if you notice, this is basically a conical pendulum problem, where you have a force that has two directions, and then the strange thing about this is that the force centripetal, Fx, is right here. So, imagine this is the case. I don't know if I can draw it three-dimensionally very well, but I'll try. So inside, so this is like a banked like a banked curve, and we're looking almost top down-ish. Nope, this is not gonna happen. Sorry, this is a bad drawing. But anyway, I think you can use your imagination. This is the curve from like a sideways perspective, and you can see the people toward you. So in other words, this section makes the curve like that. If I drew the other part. So the center, I'm trying to make a point here, is that the center is this part here, is pointing right here. So anyway, hopefully you got that. Now I need to locate you always have to locate the center, because that's going to tell you how to set up your free body diagram. So the center is going to be my XF component. That's pointing to the center, which essentially I'm going to set equal to the centripetal force like this. So we need to find Fx to find the net force. That's what this question is asking. But we got a lot of other things going on. So we need to find the gravitational force, which will be that, normal, and Fy. Okay, if you look at the normal force, it is 2 components. So what we have here is we have the normal force being broken down into, let me take this out of the problem. Force gravity and force normal. And notice that force normal is broken down into the Fx, according to this problem, and the Fy, like that. So we know that the system is not moving up or down. In other words, this system, you're not floating up or going through it. And quite technically, we are not moving in the X. Or in other words, well, actually, let me rephrase that. I don't like the way that's coming out. We're going to say our net force is in the X. So we're going to set all of our Y values to 0. So these are all the Y's. And then we're going to set the X values to mv squared over r, like that. So here we go. Our X value, the only X value we have, is this one. So we just have 1, which is set to the net force, which is mv squared over r. That was supposed to be 2. There we go. Now our Y, what we have is we have an up, I'll call that positive, Fy minus Fg equals 0. Okay. So looks like this is a pretty nice problem, because if I rearrange this, Fy is going to equal to basically the weight, which is mg, which we can find because we have a 1,200 kilogram car times 9.81. So we have Fy, which is the same as the weight, 11772 newtons. So cool. And if you think about it, this should make sense because this part and this part have to cancel each other out. So 11,772 newtons is the same as this, the Y part, 11,772 newtons. Alrighty, now what we need to do is solve for Fx, which that one's going to be mass, velocity, which is 22 meters per second squared, divided by 65. So I get 8935.38 newtons, like that. And that's my Fx. Now that is our centripetal force. We said that the F component, particularly the X, is causing the object to move in a circle. So that's our force. So the direction, I'm going to call this the negative x direction, or you can say the left. Either way, you can see that it's pointing in that direction in this case. Either way works. So to find the acceleration, it's going to be v squared over r. 22 meters per second squared over r. And I'll just write that that's 7.45 meters per second squared. It's a pretty hefty acceleration. And this is in the same direction. I'll just use left. That's fine. That's both going left. Now we need the normal and the angle. So notice that we have the parts of the triangle to solve for the angle and the hypotenuse. Because remember, this number represents the 8, 9, 3, 5, or the x component. And this is the y component, which we solved earlier. So this is the Pythagorean theorem. So I'm going to take those two values, add them up. Of course, square these. Don't worry, I didn't forget. So 11,772 squared plus 8935.38 squared square root 14,779.07 newtons is our normal force. And then we could use any part of the SOHCAHTOA, but like I always use the tangent to get the angle. So the inverse tan of our y, which is the 11,777.2 newtons divided by the 8,935.38. Now give us our angle. Which we get as 52.8 degrees. So let's write those numbers in. This becomes 14779.07 newtons, and this is 52.8 degrees, just like that. Alright, so this is how you solve a circular motion problem with a banked curve.